Hello everyone, thank you for taking the time to listen to my presentation, and today I'm going to be speaking about simulating the driving and charging of electric minibus taxis, a case study for Stellenbosch, Cape Town, Western Cape, South Africa. And more specifically, it's understanding the relationship between mobility and grid impact in the electrification of the paratransit industry. So just a bit of background before we get started. There currently exists two systems in play in South Africa. The first one is the actual mobility demand of the minibus taxis. So the community strongly relies on the taxis for transport to and from work, and it transports more than 70% of people on the road. Furthermore, it is also a source of livelihood for many people. A lot of people actually make their wages from driving taxis. Another significant issue is that there are fueling stations everywhere, but very limited charging stations, with fueling taking very quick and charging taking very long. Then the second system in question is actually the grid impact. So sub-Saharan Africa is plagued at the moment with a fragile grid network and an insufficient energy supply, and thus it has been termed load shedding, where the power is cut to specific areas. However, with the electrification of the minibus taxis, these two systems become inexpressibly linked, and so they cannot be viewed as separate anymore, but now need to be viewed as one. So how is it that we go about investigating this relationship? So firstly, it's important to understand that the taxi's behavior changes from day to day in the distance and the time that they travel. So what this means is that on any given day, the taxi can change its driving behavior based on demand and where it needs to go and where its passengers would like to go. So this makes it incredibly difficult to actually simulate. So what we do is we introduce the concept of a vehicle day. Now, a vehicle day just means instead of treating the taxis as individual taxis, we treat the days that the taxis drive as its own instance. Furthermore, we then take this normal day that the taxis would have driven and shift it from 4 o'clock in the morning of the one day to 4 o'clock in the morning of the next day to allow for sufficient charging of the taxis. So this concept also allows us to actually assess the success rate of the vehicles. Would the taxis, once they're electrified, actually be able to still meet demand? However, there's an added layer of complexity as soon as we introduce multiple vehicles driving on the same day. And this is because the vehicles now share a resource together, that being the number of chargers. So these vehicle days now become linked by the shared resource being the number of chargers. And so what we do is we also introduce the concept of a fleet day, which allows us to then actually assess the grid impact of the vehicle days. So we then went forward and built a simulation model. Firstly, it starts off with EV FleetSim, which is a software that was developed by Chris Abrams, a previous student in Stellenbosch University. And one of the outputs of EV FleetSim is actually the energy expenditure, the energy requirements of the battery of an electric model. Then I also included a simple battery model, and we took 17 taxis that were tracked in the Stellenbosch area over a month, and we used that as our baseline for everything. Furthermore, I introduced a stop determination algorithm to see when the taxi has actually stopped. Has it actually stopped in the specific charging location? Then on the charger side, I introduced the charger association algorithm, which is just responsible for assigning and deassigning chargers. And we assume the constant power and a constant voltage charging mode. And furthermore, we also introduced two scenarios with depot only charging. So there's chargers only at the taxi rank, and depot and home charging. So now we introduce home chargers into the scenario. And from this, we are then able to determine the grid power requirements, as well as the average and maximum load power profiles with the area differentiation between them. So on the right over here, you can see an example of the simulation where the downslopes is the vehicle driving, with the upslopes being the vehicle actually charging. Each colored line represents a vehicle day, with the vehicle day starting at 100% SOC on the first iteration, and the end SOC becoming the start SOC of the next iteration, which allows us to get rid of that pesky issue of SOC initialization at the end of the day. And so we simulate this until steady state is achieved, where steady state is defined as there is no change in the SOC of the vehicle at the end of the day when compared to the beginning of the day. And over here you can actually see as well that the battery model is working with the constant power and constant voltage charging, with the vehicles that go to zero being classified as unsuccessful vehicle days, and the vehicles that remain positive, as you can see in this final iteration, being considered successful vehicle days. So how then do we go about actually analyzing all of these results? So when we test with different number of charges at the depot, we can actually see that the mobility of the vehicles actually increases for 22 kilowatt depot charges and 7.2 kilowatt home charges. However, this reaches a point where the mobility in the vehicles actually doesn't change, which suggests that the taxis would need to change their behavior in order to reach 100% success rate in the electrification. So interesting to note that depot only charging requires 7 charges approximately at the depot to reach steady state, and depot including home charging, you would only need about 4 charges at the depot. So what does this actually mean practically? So this means that for 1 charger in the depot only charging scenario, we can service 1.5 taxis, and in the depot and home charging scenario, we can service 2 taxis. So what kind of vehicles or taxis can actually be electrified in this process? So over here is an example of a distribution curve showing the distance that the taxis traveled in a given day, with the orange showing the positive steady state, so the successful vehicle days, and the blue showing the unsuccessful vehicle days, and the unsuccessful being distinguished between battery, so the vehicle didn't have enough battery to meet the demand, so it ran out on the first iteration, and charging being there was not enough charges or charging opportunity in the day to do it. So what does this actually mean? So we see that for a 70 kilowatt hour battery, we have a single limitation of 140 kilometers per trip, so this is the distance that a taxi can travel on 100% SOC all the way down to 0%. However, then we see once we introduce charging in the depot only charging scenario, the taxi can travel up to 190 kilometers per day now. And when we introduce home charging, the taxis can travel up to 220 kilometers per day. So what is the grid impact? So on the left here, we can see the grid impact per vehicle, where we see a peak in the morning between 8 o'clock and 10 o'clock. And this is really exciting because this means it can be covered by solar, with a maximum peak being experienced of a single charger being 22 kilowatts. What happens if we introduce home charging now? We actually see that this peak decreases to 18 kilowatts per vehicle. However, we now introduce a second peak in the evening, as shown in the red line, between the hours of 7 o'clock and 12 o'clock. And also interesting over here is that we can see that the taxis actually travel home during the day, which could be a significant challenge. So what happens if we introduce fast charging into the scenario? So again, we have the mobility limitations of the vehicles, but now we can see that the success rate has actually increased from 79% with normal charging to 87% for fast charging. However, there is still a limitation that is reached. So what does this mean? So there's the scenario for 22 kilowatt charging. And now with 150 kilowatt charging, one charger can service 2.5 taxis in the depot only charging scenario, and in the depot and home charging scenario, it can service 2.5 taxis as well. So why is this the same? We'll see when we get to the grid. So what does this actually mean for the distances? Again, we have the 140 kilometers per trip limitation, but now for the depot only, we can increase this all the way up to 230 kilometers per day, with the depot and home charging now being all the way up to 260 kilometers per day that the taxi can travel. So over here we can see the grid impact with depot only charging, where we see 2 significant peaks that happen per vehicle in the morning, which is not ideal, with a max of 130 kilowatts. However, when we introduce home charging into the scenario, this peak reduces significantly down to 38 kilowatts per vehicle. So what does this all mean? So it simply means that we are able to test a bunch of different scenarios and not able to say which is the best scenario to choose, but rather to quantify the relationship between the mobility and the grid for a given designed system. So where to next? Testing different parameters, larger data sets, stationary batteries, vehicle-to-grid possibilities, smart energy management systems, in order to improve this success rate.